So in the last lecture, I kind of tried to give you a quick review of total station, and you will see this is happening every class. I always every class connect what you learned last class to what you will be learning this class. So in the last class, what you learn or supposed to have learned is the component of total station. And really what I want to emphasize this lecture is none of the components that you see on my screen right now is extra. Every single component on my screen, including digital theodolite and EDM and memory, a microprocessor and keyboard and display, and then finally communication with the laptop is extra. Every one of those is essential for the function of total station. Uh, so none of those is extra. So that's one thing. The other thing that you or we discuss last class is that how the total station will work and find for you the easting and the northing and the elevation of one unknown point, which is the Cartesian coordinates. And if you remember, we went through the exercise when we started from the 3D picture of my screen right now, where point A is a control point, a traverse point, where we have a total station, and point C is one of the unknown points on site. For example, the manholes, the building corners, electrical post, fire hydrant, in general, any point that you want to find the easting, northing elevation. And what happens here is that we took this 3D and then create two other views. The first view is an elevation between point A and point C, where we simply have a total station of point A and a prism on top of point C. And what we measure is we measure the slope distance and a vertical angle. And as I said, also the HA is known after we finish our traverse. And if you remember, I said, you know what? Those are not even sufficient to find our target. And remember, where is my target? My target is here. I'm trying to find the elevation of point C. And that's why I needed to measure the instrument height on one side, which stays the same for the entire setup, and it will be the same as long as I don't move my total station to another point. And in addition to my reflector height, which maybe can change from one point to another point depending on the necessity. And then finally, this is what we end up. We said, okay, here is my equation to find the elevation of point C. And really, I went through all of that last time. What I want to confirm is that in 99% of the cases, the RH we have to subtract because simply the point of interest is falling below the center of the prism. In very few cases where you are interested to, for example, find the elevation of a point to the ceiling or to the underside of the slab, where you have no option than putting the rod upside down. In this case, the RH will be added. In total station, how to solve this is we simply input the RH with a negative value. Okay, now let's go to the next scene. And the next scene is simply a plan view between A and C. And we did all the calculate last time. I kind of went through all this picture here, and we simply end up with this equation here. So we have two equations, one for the easting, one for the northing. And remember, I'm going to here try to go one by one. The easting and the northing, those are the are the coordinates of the traverse point, which they are known. While the SD and the V, those two numbers can be totally measured by total station. The last one is the mystery. The last one is the mystery, which is the azimuth of the line AC. And I think we had this discussion the last class and we said, okay, does total station by no effort, like, just get it from the box, level it, center it, does it measure the azimuth of AC? The answer was no, because simply a single reading in total station, it means nothing. If I read at one direction 10, this 10 is reference to the 0, which can be anywhere on site. It is randomly oriented. And to make total station, or to enable total station read or measure alpha, we have to do a process called backsite. Remember this name, backsite. So the backsite is simply requires 2 points of known coordinates, where total station, based on the coordinates, can estimate, calculate the azimuth of the line. And if it's able to turn the circle so the azimuth is equal to the reading at this line, it means after this process, it means the 0 of the total station is not randomly oriented on site. However, it's pointing to the north of the site. From this point on, not before this process, we can take a reading of total station, and the reading, it now has a meaning, which is it is the azimuth of the line. So please be careful. I want you to understand that if we are interested to find the easting and the northing of a point, backside is a must, And need to understand that backside, we need 2 points of known coordinates, which mean 2 traverse points. Now, I need to remind you, we never talked about the azimuth or the backside when we find elevation. And what does it mean? It means if you are interested to find elevations only, not the horizontal coordinates, not easting, not northing, it means backside is not required. And I can tell you, some of the times that we simply go to the site, our objective is not to find easting and northing. Sometimes we want to find elevations only. And if you want to find elevations only, no need for backside. Okay, so next is, in the last class, I kind of went take you through some specialized total station, some special types. A total station that is more complicated, more advanced than what you have seen in the last class. We went through motorized total station, we went through robotic total station, and then finally we went through reflectorless total station. Just to remind you, I'm not going to go through the videos one more time. Bottom line is, no matter what is the type of total station, no matter how advanced your total station is, backside, it is required. And measuring the instrument height and reflector height is still required. Okay? Maybe, yes, robotic total station can do some magic extra to what you learn, but still you have to understand it works based on the same principle. So either any of those will still use those equations. So no magic, no new equations. The equations are the same. There is a refinement of the process, or maybe, for example, there is a more advanced, but still it uses the same set of equation and require the same procedure. For example, it needs leveling, it needs centering, you need to measure the instrument height, you need to measure the reflector height, you need to do a backside. Once you've done those, then you can use, for example, robotic total station using one individual operator to finish the process. Okay, now you can see what I have done so far in a matter of 10 minutes. It's a quick revision and reminder for you of what we covered in the last class. And I find it very, very handy. And this is based on student feedback. When I do that, it kind of brings them back to last class and quickly get them into the new material. So please don't think about this as iteration, okay? It's just a nice, friendly reminder of what we covered in the last class. In today's class, we have few topics to cover. And the first thing is the types of reflectors that is being used with total station. And I know some of you maybe think that it's only one kind of reflector, I can tell you, and this is something you will understand within the next few minutes, that the different application, it requires a different type of the prism, while the idea is the same. What is the objective or the purpose of the prism? Very simple. The prism provides a reflective surface that reflects the signal back, so we can measure distance. So the prism is only required for distance. It is not required, not required for the angles. We can measure angle to anything. We don't have to have a prism on the other point to measure angles. Prisms are only for measurement of distances. Now, if I ask you, and I want someone quickly to tell me, in this picture here, in the middle, you see a total station, which you probably have seen it last term in a video, or maybe in real if you attended a normal class before the pandemic. Let me ask you, which prism among those around total station that you have seen or used? Top right, top left, bottom right, bottom left.
Top left.
I've seen bottom right.
In SAIT, you've seen the bottom right in
No,
SAIT?
sorry, not at SAIT, somewhere else. But
you know, you could have as much experience as you wish. I mean, you could have some experience in surveying or maybe in civil beyond the SAIT. But I'm asking, my question is about SAIT. So I mean, whoever said the top left picture is right. And so yes, in SAIT, you know, what you did is measuring a traverse, and the traverse was only probably 100 meter or 200 meter maximum length. And so in this case, you can use a single prism. So the name of the top left is a single prism, single glass prism. And remember, I need to remind you, when I say prism, it's not a mirror. So be careful, please, because mirror, it doesn't do the job. Because a mirror, it simply reflects the signal, and it can simply distract the signal. It doesn't go back to where it came from. But the prism is more complicated. If you look at the anatomy of the prism, you will see it's more complicated. And why is that? Because simply it reflects the signal exactly to where it came from. So you're able to get a measurement. Otherwise, if you're using a normal mirror, you know that what is the rule? The in angle is equal to the out angle, which means the signal will go somewhere else. Anyway, that's not our topic now. So I can tell you, I can confirm 100% in 99% of the application, you would use the top left one, single prism, and we attach single prism to a rod, a surveying rod that has a bubble. And when you look at the bubble, and when you look at the bubble, it ensures that my rod is vertical. And what does it mean, rod vertical? It means the center of the prism is vertically above the point on the ground, our point of interest. It means when they are vertical above each other, it means the easting, northing is the same. Remember this. When the rod is vertical, it means the center of the prism is above the point of the interest, and they have the same easting and northing. 99% of the application, we use this one. I want to take you a little bit further and take you to the picture on the top right. And I know when you look at the picture on the top right, you may see and say, okay, you know what? The top right is nothing more than, multiple of the one on the left. And I will agree. So the one on the top right is called the multiple glass prism, multiple. And in this combination here, it is 3, but I can tell you sometimes we have 4, sometimes we have 5, sometimes even we have 9. And now I'm going to ask you, why do you think do we need more than one prism? Probably it's very intuitive, Why do we need more surface area to accept the signal? The answer is for longer distances. Longer distances. So if you're measuring, let's say, 1 kilometer, you can live with one prism, because simply the signal that the total station emits, it's a laser beam. And if you guys learn a little bit about laser beam, as laser beam travels away from total station, simply the diameter of the laser beam will increase. And if you want to be able to take the measurement, you want to provide a larger surface area. So for example, the one on the right, you want to use it, for example, for distances more than 3 or 4 or 5 kilometers. Okay, so for a longer distance. Now, most of our CVT, I remember, we're not surveyors. Yes, we can do some surveying, we are not surveyor. So if you graduate and you work as a CVT in one project, which you're trying to build a warehouse and you're trying to locate the axes or the grid lines of the warehouse, you know what? The distance is very short. It can be maybe 100, 150, 200 meter, and that's why I said the top left one is something that you will see in 99% of the cases. However, for surveyor where they are trying to measure a network, for example, for Calgary, that's the job of the surveyor, okay? To measure a traverse that, for example, covers the entire Calgary, and the side of the traverse will be lengthy, will be 4 or 5 kilometers. In this case, you would use the one on the right. Okay, so the discussion so far is over for the first two, but I want to add a little bit to the one on the right, top right. So the one on the top right, I know some of you will question, Tahir, you know what, like, if I have a single prism, I know where I can shoot. There is a center of the prism, I can shoot right away to the center of the prism. Now, for the combination of the prism on the picture on the right, I'm asking you, where do we shoot? Do we shoot at the center of the prism on the top, or the right, or the left? Where? The answer is you shoot to none of them. You shoot to the center of the gravity of the three of them. And I know because of the orientation of the picture I have right now, it doesn't show you this point. However, if I turn this prism, you will see a physical point at the center of the gravity of the three prism. This is where you shoot. And simply, you will get a measurement to this point. Now, one more thing is, do you see anything below the three prism? So there is something that is below the three prism. Okay, probably I'm gonna zoom in so you guys can identify. Okay, so do you see this thing here below the prism? By the way, this is not really part of the prism. Okay, no part of it. So this is something called the Triebach. And this Triebach, when you look at it, it looks exactly like the base of total station. I'll zoom out and I'll show you. So when you look at both of them, you will see here 3 leveling screws. So we have 1, 2, 3 leveling screws. Also, you have a circular bubble, and also you have a telescope, plummeting telescope. And guess what happens? What should I use this one, or how should I use it? We use it exactly the same way as total station, which means I use this to level and center it above a tripod. So the tripod is not shown in this picture. However, you can imagine that this thing goes on a tripod. How about this thing? Does it go on a tripod? This one on the left here doesn't go on a tripod. It's attached to a rod, and the rod has a bubble, and this bubble, you use it to maintain this rod vertical. Can I get some input, please? I need some help. So I'm asking you. You think which combination is more accurate? To have a single prism with a rod, or this combination here or on top of a tripod? Which one will give you a more accurate measurement? I need some help, please.
I would assume the 3 prism would, because you have more to focus in on.
The 3 prism, yes, it can give you a longer distance, but I'm talking about the accuracy from the sense of, are we exactly above the point? Remember, we have a point of interest below on the ground. So I'm asking you, which one is more accurate? To have a rod that has a bubble, that we look at the bubble, make sure it's centered, or we have this combination or this assembly on the right sits on top of a tripod. Which one you think will yield to more accurate results in terms of being exactly above the point of interest?
The one that's on the tripod.
Exactly, sir. The one on the tripod will give you a more accurate results. Why is that? Because I can tell you, if you have some experience in surveying, Maintaining the rod vertically, it is a headache. Oh my God, look at this. What if it's so a little bit windy? And what if, your surveyor is tired? Unintentionally, the rod will be out of plumb and you have some errors. However, when you install this assembly on the right on a tripod, you make sure 100% that the point is above the point of interest. But here is the point. Here is the discussion. I want you to understand. Oh my God. So it means if I want to survey a manhole, do you think I'm going to get a tripod, level it, center it, and put the prism on top, back, and then on top of a tripod? Is that practical? You know how long does it take to level and center a tripod of a point on top of a point? Can I get some help, please? I'm asking you, do you think I'm going to, for example, I want to find the coordinates of a manhole or a building corner or any feature on site, let's say also a fire hydrant. Am I going to bring a tripod and set the tripod on top of the manhole and get this assembly, level it center above the point to get the XYZ? Or that's too much, that's overkill?
Not likely,
That's
unless
too
it's like
much
a
time.
long way away, or you're setting up a new benchmark maybe.
Exactly, sir. So here is the point, and that's the point I'm trying to make here. Although this one on the right is very, very accurate for being above the point, but is used only for the control network, for the traverse point. However, once we start our survey to locate some points in space, like building corners and trees and stuff like that, we do not use tripod, rather than using a single prism on top of a rod. I know maybe at SATE, we don't do that for this, only for the sake of time, because it takes a very long time to do that. Okay, so maybe for the purpose of the exercise, I know some teachers, they measure the traverse with a rod, but I can tell you, if you want the highest precision, then for the traverse, you would use the assembly on the right, and not necessarily to be a three prism. It's even a single prism on top of a tri-back on top of a tripod. Okay, so that is really what I want to emphasize and get you to understand. Now let's move on to our next our next prism, which is the bottom left. So the bottom left, I kind of gave you a very quick introduction about the prism last class or last lecture, and this is called 360 degrees prism. And you can see it looks different from the previous ones, because simply you can see it doesn't really have a plastic enclosure, and you can see it's more complicated. And the point is, without giving you so much physics or math, regardless the direction in space where the line of sight came, it will go through inside the combination of the prism, and it will go back to exactly where it come from. And as I said, this is very convenient to be used in conjunction with robot total station. Because if you remember the video that I showed you last class, it doesn't matter what is the orientation of my prism. And that's why my surveyor wouldn't spend any time or any effort to rotate and make sure that it faces your total station, because simply he has so many other jobs to do. For example, he has to make sure, or she has to make sure, that the rod is vertical, so looking at the bubble tube. Number two, has to input some information to the total station. Let's say I am on top of a manhole, and then finally shoot me now. It means don't focus up, just do other things. So hopefully you understand and believe that the bottom left 360 degrees prism, it works fantastic and very convenient with robot total station. Finally, let's go to the most interesting one. So the most interesting one, to be honest, is the bottom right one. So the bottom right one is called paper prism or sheet reflector. So I mean, different people use different names. As far as I know, it's called sheet reflector or paper prism. And look at the name, paper prism or sheet reflector. So it's kind of a stamp, and it can be as tiny as, I think, ½ inch by ½ inch, and it goes as big as 3 inches by 3 inches, depending on the distance you want to measure. Okay. And what's good about this one is you can permanently stick this one on one point in space. Let's say I can go to one wall and I can stick this with, for example, with epoxy, or I probably produce a bracket and I can attach to one point in space and I can leave it there forever. Okay. Now, why this paper prism or sheet reflector is fantastic in some application? Here is the point. So if you guys remember from the last class, I kind of showed you, some application. We call it deformation monitoring. So, I mean, I still have a presentation here, and probably I can show you some picture right away. You guys look at this. I mean, if you look at this slide here, so we talked about this application where we're trying to build a high-rise building, and we have to dig down and we install retaining walls, and those retaining walls are very sensitive. If they move without notice, then that's a serious problem. And why we need to monitor them and make sure they are in a stable condition to avoid any fatality and any failure of the retaining wall. Okay. So anyway, I'm not going to go and repeat everything I said before. Really, my focus right now is to show you the paper prism is the best for those applications. Remember, if those paper prism, because the way they are, for example, they have a shorter distance. Maybe it could be 100 meter or so, which is good for this application. But they are very cheap, very cheap. So maybe a few bucks, and then you can add many of them on these walls that you see. We can make a grid, maybe a point every 4 meter or 5 meter XY grid on top of the wall. And so we stick them on the wall. And if this hole in the ground stays for 2 years until we finish all the footing and we simply build the main floor, and in this case, we can leave them permanently for the duration of 2 years on the wall. We don't have to take them because simply we cannot take them. Anybody knows why we cannot take them down and put them every day like what we do normally with other prisms? Just try to think. I'm trying to. Any
Because
guess?
the point of them is to track how much it shifts day to day or even week to week.
Exactly, sir. So if you take the prism and go back home and come back next day, put them, which is impractical, then there is no guarantee that you can go to the same place. And if there is no guarantee that you can stick them on the same place, guess what? The errors, because simply, how do we quantify the deformation? How do we measure deformation? We measure the coordinates today. We call this initial measurement, and we measure them every day. And we reference our measurement in one day to the first day. And this what will give us the change in coordinates, and that will give us the deformation. So I'm asking you, if we're not able to precisely put our prism at the same location, it means this error can give me a false indication of the movement of the wall without even the wall moving, or maybe I'm lucky I put the prism and I got zero measurement, while zero difference, I'm sorry, while the wall is already in motion. So hopefully you understand the paper prism, because of their price, because of the way they design, it is best for this application. You stick them on the wall, let's say using epoxy, and you leave them there for the duration of the project, let's say 2 years. You don't have to take them down. Does it make sense, sir? Does it? Are you following?
Yes.
Now,
Yep.
One last thing before I leave this part here. You guys know, if I use paper like a single prism or maybe a multiple glass prism or 360 degrees prism, okay? You know what does it mean, the reflector height? So the reflector height, for example, of the paper prism is from the ground to this point, okay? Hopefully you understand this. And for multiple glass prism, my reflector height is to this point, okay? And let's say for 360 degrees, let's say the prism to this point here, the reflector height. Now let me ask you, what is the reflector height for paper prism? Please think about it before you answer. What is reflector height if I'm using paper prism in a deformation monitoring application?
0.
Thank you so much. It's 0. Why is that? Because you can see this is the center of the prism, and this is the only prism that you can attach to the same physical point of interest, which means there is no physical distance between the point of interest and the paper prism. So the reflector height for paper prism is equal to 0. Thank you so much. Now, guys, I'm going to take you to another discussion here, which is super important, and I'm not sure even if you already hit this point last year. Okay, so let me explain for you what does it mean. Let me add here a brand new. I think I should be able to add insert. So insert a blank page, and it doesn't really matter where. So here is a blank page. Now, you know what? I'm gonna go a little bit off and to prove my point. So let's say, guys, I have here a point on site, and this point here, I'll call it point A. And let's say I have another point here, I call it point B. Very simple surveying problem, okay? And, you know, I have 2 points, and I'm asking you, you are my surveyor, I'm asking you, could you please find for me the distance between A and B? And you will say, yes, sir, okay? And what you will do is, based on what I taught you so far, you'll say, okay, you know what? I will get my total station here, let's say here, okay? I put my tripod here on point A. I put my prism here on point B, and I will simply measure the line AB. No problem. Piece of cake, easy. Now the question is, which will make things more complicated, what if in between here I have something in between? So this guy here, let's say it's a building. It's a building, okay? I want you, I guess, because sometimes some of you guys are hard to imagine or understand why, if there is a building, it's not easy to find the distance AB. Can anybody tell me why it's very difficult if there is a building in between? It's hard to find or measure the distance AB.
You don't have a clear line of sight.
Perfect, sir. Thank you so much. You saved my time. The secret is line of sight. Line of sight, it means from one point I can observe and can see the point on the other side. Now, can I just quit my job and say, no, sir, I cannot give you the distance, or surveyor are smart and we can simply do something smart? Let me show you how, okay? Here is the thing, the answer will come from mathematics before it comes from surveying, huh? So the answer will come from math. So let's say, guys, let's say that's a plan view, huh? Maybe the first one was kind of elevation, something like that. But let's say this is a plan view. So I have point A, I have point B, and in between there is a building. And what to do? Some of you and some of my students in the past, they say, you know what, Tahir, why don't we measure, you know what, this dimension here? Let's measure this dimension. And then let's measure, let's say x1. And then let's measure this distance here, okay? And so on the building, so that's x2. And some will say, okay, you know what, let's finish it. And let's measure x3 from here to there, x3. And finally, your distance is nothing more than adding the 3 of them. Anybody disagree of what you see on my screen?
Seems like a lot of ways to end up with errors.
I mean, is it correct? Like, is what I'm saying is correct or wrong? Okay, I'm not gonna spend like I'm going to give you the answer. So the thing is, everything on the screen is completely wrong, and I'll tell you why it's wrong and why it's impractical. So wrong because simply the 3 distance x1, x2, x3, they are not along the line. They are zigzag. So you can tell you kind of measure x1 in between A and B, and then x2 has different direction and x3 has a different direction, which means adding them together, if you're able to measure them, is not correct. Number 2 is, I'm asking you, how would you measure x1? Like X2 is easy because simply that's a building. I will simply go on the side of the building, have a measure tape. I can measure X2. But I'm asking you, how would you measure X1 or X3? Think about it, please. Is that something possible or impossible? Whoever said line of sight would know. That's a key for you or clue for you. Are you able to measure X1 along the line AB or X3? Or that's impossible because simply you're not able to see from A to CB and the opposite. What do you think?
It's impossible to measure
It's impossible. So guys, here we go. Okay, here we go. I wanted to point out that this proposal is wrong. So let's get rid of it. Okay, so I'm not going to do that. Okay, so how about another proposal? So you guys know from math, from math, not from surveying. If I have point here and this point here is point C, okay? And remember, point C doesn't have to be a specific point. All it has to be is from point A, you should be able, from point C, you should be observed. You have a line of sight to point A, and also from point C, you have a clear line of sight to point B, okay? So remember, point C doesn't have to be a specific point. It can be any point on site where you have a clear line of sight to point A and B. Let me ask you, what if I have my total station here? Okay, and remember, still a plan view, but I'm trying to show you that your total station is here. And let's say I have a prism here, okay? What can I measure if I do that? I can simply measure distance from C to A, correct? Which is a slope distance, and I can measure a vertical angle from C to A. And I can repeat the same thing between C and point B. So I have a prism here, and when I have a prism here, I can measure a slope distance and also a vertical angle. I'm asking you, you think that's sufficient to calculate? And I'm very precise. I'm not saying to measure AB, I'm saying to calculate AB. A distance, a vertical angle, a distance, a slope distance, and a vertical angle. Is that enough, or I'm missing something? Go to your math
You're
class.
missing the horizontal degree between the two of them.
Thank you, sir. That's exactly what I'm pointing here. So that's really what I'm missing here, which is the angle between A and C and B, which is, we can do that using total station. Take a reading, and get the difference in reading. I'll get the angle. Then finally, what to do if I have all this measurement? Watch me, please. You know what? Here I'm going to do it. You guys know something called cosine rule. And cosine rule is not very difficult. I don't have the proper tool to write it, but here we go. I will do my best. So AB here is equal to SQRT, which is square root of AC squared plus CB square minus 2 AC and then CB, and then cosine the angle, let's say theta, where the angle theta is simply here. So I'm going to write here, this is the theta. Okay, so I'm asking you guys, I'm asking you right now, you can see using some mathematics equation, I can solve for a surveying problem using a very simple math equation. I think I'm missing a bracket here. So this is my final. So that's my final bracket, which closes the square root. Okay. Are you guys following? That's a cosine rule. Now, let me ask you, what are my options? My options are, I can go to the site. I can simply level center my total station over point C. I can get all the measurement. And when I go home, I can simply get all the measurement and I can use them in the equation you see below. So that's option number one. However, I don't need to do that because simply a total station has a microprocessor and simply it can do this on my behalf. And that's why here is the point. Okay, let's move on to this topic here. So this topic here is called special programs in total station. So some of you may think by now that total station is simply, it can only measure angles and distances, which yes, this is what it can do. But because I have a microprocessor, it can take you to a more complicated questions. For example, like final coordinates. And this is one of the special programs in Total Station. Look at the name, called RDM. This is exactly what I showed you a minute ago. Remote distance measurement, RDM. And what it does, it simply measures the distance between 2 points and also measure the elevation difference between 2 points. And I will be specific. This is your point A, and let's say this is your point B here, okay? And where is point C? This is your point C, the third point. And using the measurement, we can find the distance between A and B, in addition to elevation difference between A and B. Just like a click, like what you can do is, you don't have to go to the office and download the data to estimate the distance. Rather than just right away on site, there is a little program you start, and it will guide you through to find your unknowns. And in this case, what are the unknowns? The distance between A and B, horizontal distance, in addition to elevation difference between A and B, okay? Now, along the same line, we have another problem that kind of my surveyor will encounter on site on a daily basis. And this is, I'm going to give you the problem same as I introduced for you this problem here. So this problem here that my surveyor is trying to answer this question. How about another question? Okay, what if I have a point which is inaccessible? So guys, we talked about, I think last class, when we talked about reflectorless mode, and we talked about inaccessible point, a point which is hard or impossible to send a prism to this point, okay? And so in our case here, I will I'll give you an application. Let's say I have a road, and we have here that's power cable. So this one here, this is a power cable, and we want to find this distance. This distance is very common in civil engineering, called clearance, okay? Or I think I think also called headroom, okay? So the headroom or the clearance, very important for so many applications. Now I'm asking you, how would you find the clearance or the headroom between a cable and the road? Okay, so you can think about it, and some of you will say, okay, you know what, Tahir, you taught us something called reflectorless mode. So I have my reflector here, my total station here, and simply, if you have a total station, you can use the reflectorless mode, because simply you don't need a prism at this point, okay? And if I'm able to measure here the easting, okay, the easting, northing elevation of this point, later on, I can simply bring someone here below the cable with my prism down here, and I can find also the easting. I can find here the easting and the northing and elevation of the point below. Now, finally, if you know the elevation of the cable, you know the elevation of the ground, then this will be your delta H. So let's say this is H, for example, this is E1, E1, N1, H1, and this one is E2, N2, and then finally H2, then your H1 minus H2, this will give you the clearance. But remember the last class, what I said, is there any condition about this distance? Does it go forever, like between the total station and the point in a reflectorless mode? Does it measure, let's say 200, 300, 400 meter, or it has a limitation? Anybody remembers?
100 meters.
Thank you so much. That's correct. It's about 100 meters. Now, let me ask you, sometimes you're right. If the distance between the total station and the cable is less than 100 meters, congratulations. No need to do anything. Just use your total station in reflectorless mode and find coordinates. Now, the question is, what if this guy is more than 100 meters? Okay. What if my slope distance is more than 100 meters? What does it mean? It means you cannot use it in a reflectorless mode. Cannot. So what's the other option? Here is the other option. Okay, so I'm going to show you right now a program which comes from the math background that allows you to find the clearance. If your distance is more than 100 meters, it means you cannot use reflectorless mode. Now, not very difficult. It comes again from math. Now, let me ask you, if this distance is more than 100 meters, can I still measure the angle, like the vertical angle? Remember, angles don't need any prism. As I said in the beginning, the angles, you can just have your line of sight to the cable and you can measure the angle. And here we go. So we can measure this angle here to the cable. I will call this one, let's say, V sub C. So that's the vertical angle to the cable. Now, can we also measure the vertical angle to the center of the prism below, like doing this? Can I measure the angle to the center of the prism? Yes, you can do that. However, since I have a prism here below the cable, then also what I can do is I can measure my SD. Remember, the distance is not available until you have a prism or within the reflectorless limit. And remember, with those measurements, so now I have one angle to the cable, I have a slope distance to the prism, I also have the angle here, I'll call this one V prism, so V for the prism, and then finally this distance called the reflector height. If you think about it, you will see with these measurements, so I have one angle, two angles, SD and RH. You see, if you know about math, you should be able to find the clearance. There is a relationship between them. Without taking your time into much math, because you're not required to do that, here is what you have. You have another program called REM. Let me show you in 3D. So we looked at RGM, remote distance measurement. Also, we will look at REM, remote elevation measurement. Look at this place. So you can see here is my situation. I have an electrical cable, which I cannot place a prism over there. The distance is more than reflectorless mode limit. And simply all you have to do is you shoot the prism, and under the prism, you bring, under the cable, straight under the cable, you have a prism, whether on top of a tripod or maybe a rod. You do another measurement to the center of the prism where you can find the distance. And again, if you think about math and if you're good at trigonometry, you should be able to find the height or the clearance. Any questions so far? Any questions so far? Okay, so I have few things to mention and just kind of close this part before the break. It's not going to take us like long time. So here is the conclusion. Total station, some of you maybe thought it can collect raw measurement only. And if you remember, what are those raw measurement? Those are slope distance, vertical angle, and horizontal direction. Yes, it can do that. Okay, and we collected those raw measurement when we survey the traverse. But remember, after you survey the traverse and adjust the traverse, it means remove all the errors and the angles and distances, and now you have coordinates. Now we can start our regular survey, and we survey manholes, electrical posts, any feature on site. And in this case, my total station can simply put all the raw measurement in addition to some input, like for example, the occupied point coordinates, the reflector height, the instrument height, and I already took you through the math equation. And finally, you should be able to find the easting, northing elevation. So one of the other products that total station can do is it can simply provide you with coordinates. And for example, if I zoom in, this is one of the total station outputs. Okay, and this is something we will start either today or even next class to deal with. So those coordinates are measurement using total station, not raw measurement, but processed coordinates. Now, what is the third way that I can use total station for? Here we go. We can use total station with a special program, like for example, the REM or the RGM to give you an answer for one specific question. I want to confirm before we break that the number of special programs is not limited. Okay, so for example, RDM or REM, those are available and one of the oldest program on Total Station. If you even use Total Station that was built 20 years ago, you will find RDM and REM. However, with the evolvement with the processing power of the Total Station, things have no limit right now. If you notice from the last class, when I showed you the video where you can survey a dirt pile, like a stockpile, where you can find the volume, not on your laptop, however, it's on site. And to do so, I will show you, we can do that, and I will show you how to do that in our class. But you will see, we do it how? We download the data, we use a Civil 3D to find the volume. This is maybe for some advanced Total Station, is not even required, because we can perform those calculations on a special programs on Total Station. With this note, I kind of finish all I wanted to say, talk about Total Station, and hopefully I gave you kind of a quick refreshment of Total Station. Before I break, does anyone have questions before we break? Let's see. Please raise your hand if you have any question before we break. Looks like you guys listen, you have to understand this. I mean, let's put it this way before we continue. Guys, you understand, you have some challenges for sure from your perspective as a student in online education. You have a challenge. But I'm going to tell you one of my challenges as a teacher in online. The problem is all I see right now is I can see Daniel picture, I can see Adrian, I can see your, Gian picture or photo, but I don't see your reaction, your gesture, okay? And if you guys are so quiet, I will be wondering, are those guys following? Do they care? I don't know. And that's why I'm kind of struggling with this. Really, when we were in class, this doesn't exist because I can see all of you. I can look at your face, and my experience tells me, oh, you know what? Those guys are not following. Probably I have to say it one more time. But here is the point. When we are online, I need some very little confirmation that, yes, we're following, as simple as that, and you can mute yourself, or you can say, stop, I'm not following, okay? So please do that. Feel free to interrupt me if you are not following. Now, if you have no question, then time for a break. I will see you guys back here at 11:05. Thank you so much. We'll see you in 10 minutes.
For the
Daniel?
reflectorless mode, where you're beyond 100 meters and you have to use the secondary reflector, that secondary reflector has to be directly under the point you're measuring the clearance to, correct? Like you can't have it in front or behind, or else that won't work.
So if you are in reflectorless mode, you don't need to do any of this business. If you are in reflectorless mode, I'm sorry, let's go back to the slide. For sure, you need to measure the point on the ground, so you should be able to find the delta in elevation. So what we do is we do our best to, our helper should do our best to align themselves to be under the point of interest as much as you can. Remember, I know that this process will have some sort of error, but probably if you're careful, the error will be acceptable. Okay? Did I answer your question?
Yeah, more or less. So basically, you have to be as close to underneath the point of interest as possible to get an accurate measurement.
And I can tell you, in many application, people they use their eyes to align themselves to the underside of the point of the measurement. I know it's not 100% precise because you cannot be perfectly under the point, right? You cannot be perfectly under the point. But again, do your best. And again, if you are within plus or minus even 5 centimeters, then you should be okay. For the clearance estimate, let's be exact. Okay, so again, we'll see you guys here back at 11:05. 10 minutes break. Thank you.